Okay, so this somewhat general title, Future of the Mind, actually divides in our hands into three areas, one of which I'll talk about. First, the developing mind, where we look at the impacts of certain controversial drugs, not least Ritalin, on how they impact not just on the brain itself, but also on the cognitive sciences through to policy and educational practice in the classroom. The mature mind, a small question here, how might the brain generate consciousness? I'd be delighted to talk about either of these two areas in the tea break. And although these are encompassed, if you like, under this notion of the future of the mind, the real one I want to talk about this afternoon, and for which we have core funding from the James Martin Institute, is the is the degenerating mind, where we are tackling the issues, and that's why with great perspicacity, Ian has programmed this so brilliantly, so the one segues so well into the other from that last presentation. You might wonder why we're doing both Alzheimer's and Parkinson's, and I think that really introduces why we are, I think, different, and that we take as a starting point that you often find a co-pathology with Alzheimer's and Parkinson's. Yes, of course, they're separate diseases, and of course, they're treated conventionally by different drugs that in turn combat the dwindling levels of the transmitter, dopamine in Parkinson's, Alzheimer's in acetylcholine in Alzheimer's. But our view is that the two actually have much more in common as diseases than they have that distinguishes them. So what we're doing is looking at neurodegeneration, and I'm going to use that term as a blanket term that encompasses both Alzheimer's, Parkinson's, and indeed motor neuron disease. So our long-term goal is the following dream. Two scenarios. Scenario one, you could discover a marker in the blood. This would mean that you could go to the doctor, like you might go for breast screening or osteoporosis screening, and have a routine blood test, and the doctor would say to you, I'm afraid, even though you have no symptoms, a marker is elevated, indicative of a neurodegenerative disease. Now, that might seem something rather gloomy, but if you think about it, it would actually, well, that doesn't sound very glamorous, it would actually be quite helpful, because you could then perhaps have a more effective treatment, even with existing medication. You could start the medication early, and I think no one would deny that would be a welcome prospect. Also, again, without sounding too gloomy, you could plan ahead. Say you were having Parkinson's disease, and you knew in 2 or 3 years you're going to be in a wheelchair, you could plan the world cruise now. Yeah, well, I know it sounds gloomy, but nonetheless, it's, you could actually, some people might wish to do that. And I toss over to the ethicist whether or not this would be a welcome prospect for people or not. And finally, given he has no papers to review nowadays, that's one of those. And the other is the possibility of pre-symptomatic medication, which I'll talk about in a second. But nonetheless, it would help drug companies, because instead of possibly having a separate placebo group from their treated group, the patient might be their own control. If you could take a blood sample every month or two, you could actually see two people starting off at the same clinical stage, the rate of decline in the placebo versus the drug group that would actually validate the efficacy of the drug on trial in a much shorter and faster and cheaper way. So although it doesn't sound very glamorous, and it's not a magic pill that's going to cure you of Alzheimer's or Parkinson's, it is nonetheless quite appealing to develop a surrogate marker. That is scenario one. Well, so far, we've made some strides on this, and this is some hot-off-the-press data from Professor Hooper's clinic in Leeds. We've obtained some serum samples from controls and Alzheimer's with respectively 9795 numbers, and looking at a particular fraction that lies between 10 and 30 kilodaltons, we have found that in this fraction selectively, we do see, using a test that we have devised, a highly significant difference shown here with an adjusted baseline between the controls and the Alzheimer's. This is the controls. And this has, very pleasingly, a significance of p.0001. We've then subjected this to massive scrutiny with the medical statisticians, and the bad news is that the p-level is now reduced to 0.001, but we can now with great confidence say it's not due to any other factors at all. They've done the things that medical statisticians do with all the patient data that they have. So this we find very encouraging. Again, I won't labor a non-specialist audience with details of the actual test, but I'd be happy to explain, as would Sherry or Amy, I'm sure, in the tea break. Scenario two, to discover a means for stabilizing soul loss. Here you can see what is well known, that at the moment, certain drugs such as Aricept can stabilize soul loss for a while. But the reason that NICE have rejected that, for example, is because it is not a cure. Even though it might prolong life, prolong quality of life, the mandarins at NICE don't find that very persuasive. But wouldn't it be wonderful if you could if you had a drug that blocked any further decline? So you could go to the doctor and they'd say, okay, the bad news is, I'm afraid, as you know, you've got Alzheimer's or Parkinson's, but we now have a medication, and if you take this medication every day, even though you're having memory problems now or movement problems now, it won't get any worse. And that would be, the medics in the audience would realize that would be absolutely fantastic, and people would, I won't say die for, because obviously they wouldn't die for it, but they would do metaphorical of that if only one had a way of just stabilizing cell loss. Nothing glamorous, nothing exotic, just stopping any more cells dying. But that is predicated on the big question that, to my own view, is ignored by most other people researching in this area of the big question, why did the cells die in the first place? Yeah. So my own view is that that is the best approach, is to try and ask the question, why does the cells die in the first place, rather than just closing the door after the horse has bolted and tackling the symptoms. So what we've tried to do here is to explore that question with a view to providing a new approach to stabilizing cell loss in neurodegeneration. As I mentioned, we start with the premise, often ignored by many, because it flies in the face of normal pharmacology, where you have these separate transmitters, that Parkinson's and Alzheimer's can coexist. And actually, this is the back of the brain, this is the front for those of you who are not demon neuroscientists. You can actually see there is this kind of hub of cells in the brain that have features very different from all the other cells in the brain, to the extent that they have a different embryonic provenance, even from a different plate in embryonic development. So we know the difference is very fundamental. And the view that we have in the lab is that this could provide a clue, because it is these very cells that are the ones, even though they have different transmitters, that are lost in Parkinson's and indeed Alzheimer's. And you can see that what might happen is you could have damage just here, you'd get Alzheimer's, damage here, you'd get Parkinson's, more extensive damage, you'd have both. Yeah. Now, what's really exciting, even though these different colors represent different transmitters, another potentially toxic chemical is common throughout this hub. Now, I won't bother telling you what it is, but it's a chemical that is there irrespective of the transmitter that is used. And my own view is that there must be some kind of coincidence here. If these are the primary cells lost in Alzheimer's and Parkinson's, and they're adjacent, and you can understand the co-pathology, and they do have a chemical in common, it might be interesting and helpful to look at what that chemical is. Now, what's interesting about these cells is that, unlike the other cells in the brain, one of the very distinctive characteristics is that they have retained their ability to grow. They've retained their sensitivity to so-called trophic factors in a way that the other cells have not. It turns out that this toxic, potentially toxic chemical is indeed a trophic factor normally. So we have the idea that neurodegeneration is an aberrant form of development. And what happens is, in development normally, this is a synapse, the gap between one cell and another, with these little chemical messengers enter into a molecular handshake with a target protein, so-called receptor. And I'm sure you're familiar with that notion. So the idea is that during development, this chemical is working away, but when it might be reactivated during damage, the cell wants to grow again. Other cells in the brain don't do this, but this hub of cells can. They do so, and it's this interaction, this molecular handshake between the normally trophic agent that has become toxic because it's in a mature cell that causes all the damage. So this is some work that Sherry did, showing what's very interesting, that this toxic chemical not only acts on a target that we've identified, a particular receptor, but it actually enhances, as a feed-forward mechanism, it enhances the number of its own targets. These are control cells, and these are two. There's one variant of this peptide, this chemical, and this is the more potent one. But you can see, I hope, this shininess around the cells showing an enhancement in the target on the surface of the cell. So this toxic evil chemical is giving rise to further targets so it can perpetrate its toxicity even further. And that's what we think is neurodegeneration. So the more the chemical binds to the target, the more chemicals released and made. And the more the chemical binds to still more targets, and on we go. So what you need to do is to intercept that interaction, and then we'd have the dream. We'd have scenario 2 realized. That's what we call neurodegeneration. So, that's a bit me showing off my PowerPoint skills. So the toxic chemical can be blocked. That's normal cells. This is exposure to the chemical, and that's applying the blocker. And so how can we put those two scenarios together for neurodegenerative diseases? Well, imagine these two scenarios. One, the marker detects neurodegenerative symptoms before the symptoms appear. So, and that in itself would be helpful. You go to the doctor. But say you go to the doctor before the symptoms are there, and they say, well, the bad news is you've got this neurodegenerative condition. But imagine now we have the medication suggested by this new approach arresting further neuronal death, and that would be prevention of symptom onset even before it came on. And that would be not a cure, but an effective cure. So that's the dream that we're doing. So because the red card has come up, our immediate goals are to identify this blood marker. We have ideas what it might be, to increase the sample size to show how specific and selective it is, and finally to evaluate and justify our hypothesis by looking at human brain tissue, both quantitatively and qualitatively, by looking at levels of the chemical and also histological features. Finally, this is to show, in generally, the three approaches that we have, how we are networked into not just other science, but also into politics and education policy and the like. And finally, the current clinical collaborators shown here, without whom, of course, it would be impossible. And finally, some suggested collaborators within the school, and I welcome the chance, as I'm sure Sherry and Amy do, to talk with you, especially people from these institutes, as to how we might interface with you. Thank you very much.